Now that we spent a fair amount of time talking about the ForkJoin pool and the common ForkJoin pool and managed blockers and so on, it's time to turn our attention to a bunch of different ways to actually program ForkJoin pools. And we're going to look at a couple of different programming models. In fact, we're going to look at 4 or 5 different programming models. And each of these models will show different techniques, different patterns, and so on of how to program with ForkJoin pool. So the way this is going to work, there's a cool example that you can find in my EX22 folder in my GitHub repository at the link at the bottom of the slide. And this particular example does a really nice job of apples to apples comparisons between a bunch of different ways of programming ForkJoin pool. And as you can see here, the different models we're going to look at are going to have different pros and cons. Some are easier to program, some are harder to program, some incur more stealing, some incur less stealing, some copy more data, some make more method calls, and so on and so forth. And you'll get a feel for the pros and cons of the different approaches. And some that do less stealing often run faster because they're able to do the processing without having to spend as much time stealing, which turns out to be a win in many situations. Okay, so let's go ahead and take a look at this. We're also going to use some Java functional programming features wherever possible to simplify the code. You don't have to use functional programming features with Java ForkJoin pool. It's really part of Java 7, which was before the functional programming features came out. But in my experience, they work together quite nicely. And naturally, the newer versions of Java, modern Java as it's called, integrate these functional programming features atop the common ForkJoin pool in very cool ways, as we'll see a little bit later. This particular program is going to perform a bunch of operations on so-called big fraction objects. And let's spend a second or so just talking about what is a big fraction. So a big fraction is a class, and this class is something that you can also get in my repository, and it supports arbitrary precision fractions utilizing so-called big integers for the numerator and denominator. And big integers are basically arbitrary precision integers. You can make them as big as you want. There's a bunch of factor methods in the big factory class for creating so-called reduced fractions. So for example, if you have 12 24ths, that could be reduced to 1/2, or 44 55ths, that can be reduced to 4/5, and so on and so forth. There's also factor methods for creating non-reduced fractions and then later reducing them if you want. There's a whole bunch of methods to perform arbitrary precision fraction arithmetic. So if you ever need to multiply 18/4 by 2/3, you'll get 3 as the result by using these methods. And then you can also create mixed fractions from improper fractions. So for example, as you see here, 18/4 can be reduced to a so-called mixed fraction. The 18/4 so-called improper fraction, which is a funny name, can be reduced to be 4.5, which is the mixed fraction. The main program here is going to reduce and multiply big fractions by, of course, using the Java ForkJoin framework. And what it does is, and we'll look at this code in more detail, but basically in a nutshell, what it does is it uses a generator method from the stream interface called generate, and it's going to make a whole bunch of big fractions. And it's going to use a random number generator to generate very large random big fractions that initially start out being unreduced. And then it's going to limit the total number of the fractions that are generated to some constant, which in this case is S max fractions. And then it will collect the results together into a list of big fractions. So that's just basically to generate common data that all the different various ways of programming that ForkJoin pool will work with. Here's what the make big fraction method does. It's a factor method that creates a very large and random big fraction. It uses big integer, and it makes a random numerator that's uniformly distributed over the range 0 to 2 to the 150,000th minus 1. And I think you'll agree with me, that's a really big number. So it's going to make a gigantic big numerator, and then it's going to go ahead and make a denominator that's also randomly generated between 1 to 10. So that's the numerator and denominator. And it's going to put those things together using the value of factor method that's defined in big fraction class. And it's also going to pass in whether you want to reduce this big fraction. We are not going to reduce it. I believe we do not reduce it. Let's see if we reduce it. We do not reduce it by default. So what we do then is we're going to create ourselves a function, which is a Java 8 functional interface that's going to map big fraction to big fraction. And it's going to take in a non-reduced big fraction, and then it's going to reduce that big fraction, and then it's going to go ahead and multiply that reduced big fraction by another big fraction constant. So that's the computation that'll take place. And believe me, that computation takes a long time because these are very, very large numbers. And then the final thing we do is we test all the various ways of doing the ForkJoin pool to perform these big fraction reductions and multiplications. And we'll talk about each of those techniques shortly. Here's how we do this. We go ahead and have some kind of helper methods. And these methods basically take in the fraction list of those randomly generated fractions, takes in the function to perform, and then it allocates a new ForkJoin pool and goes to town and performs the operations. And naturally, we're going to time everything so we can see how long it takes to execute. And we can compare and contrast to understand why some approaches work better than others. Each of these helper methods here uses a different means of applying the ForkJoin framework. And we'll take a look at each of these in turn so you can learn the different programming techniques and what the pros and cons are of each one. The apply all iter method uses work stealing to disperse tasks to worker threads. The apply all split method uses recursive decomposition to disperse tasks to worker threads. We'll talk more about what recursive decomposition means in a second. And then finally, we have one called apply all split index, which uses an optimized variant of recursive decomposition to disperse tasks to worker threads. And each of these approaches, as we'll see, have trade-offs in terms of complexity and efficiency and data copying and all these other good things. Each of the helper methods gets its own ForkJoin pool that will default to the number of processor cores. Remember, the common ForkJoin pool by default is always one less than the number of processor cores. But if you just make a new ForkJoin pool that's a custom one that you create, it's not the common one, it defaults to the number of processor cores. So that's the end of the overview. Now what we're going to do is we're going to walk through each of the different implementations and show how they work and then compare and contrast their pros and cons.